Hello, Houston. Sitting here looking so relaxed, you should see the chaos that goes on before we start each time. It's amazing we make it. We were most of the way through our journey involving the statistics, and we've been talking so far about descriptive statistics. And today what we're going to do is finish inferential statistics very briefly and predictive statistics, and then move on into our real topic today, which is developmental psychology. So if we can put the first computer image up on the screen, let me talk to you a little bit about this. In essence, what we've got there is a normal distribution, and if somebody in the studio can get me an image on the monitor here, it would be very helpful so I can see what I'm talking about. The normal distribution shows up so regularly and so predictably among us humans that in fact statisticians have actually studied that distribution itself. And there turn out to be some amazing features or things about that distribution that always tend to show up. For instance, if we look at the normal distribution, and you will remember last time I was talking about the standard score, which doesn't show up here. I'll get to it in a minute, I guess. The normal distribution has a feature on it, specifically the idea that 68% of the data falls within one standard deviation of the mean. So on any given normalized set of data, any data that is normally distributed, we can say basically that 68% of it falls within one standard deviation of the mean. What that means is, I love PowerPoint, 68% falls within one standard deviation of the mean. What that also means then is that we can actually use that to calculate things like percentiles. I'm not going to show you specifically how to do that, but we can in fact do that. We can use where you are in the distribution to calculate what percentile you're at in terms of how the overall data is determined. As an example, on the exams that I give in class in intro, the average that we get is about 30. It may be 25, it may be 30 on a given exam, but the standard deviation is regularly about 5. It's somewhere between 4.5 and 6. So for the sake of argument, let's just assume that it's 5 and the mean of the distribution is 30. What that means is that on average, on the exams that I give in class here, 68% of you will score within 5 points of 30. That is, you'll have a score between 25 and 35. If the class average is 30, you will have a standard deviation of 5 points on the exam, and that means 68% of you will fall within one standard deviation of the mean. That is between 25 and 35. As another example, the SAT test that many of you took to get into the University of Houston, for instance, has as part of it the existence of a 500 mean and a 100-point standard deviation. So in essence, what that means is that for when people take the standard SAT test, about 68% of the people will have their scores fall between 400 and 600. The mean is 500, the standard deviation is 100. Again, about 68% of the people who take the SAT will score between 400 and 600. About 95% of the data falls within 2 standard deviations of the mean. Okay? Now let's back up a second and ask a question to test your understanding here a little bit about what we're doing. If I say that well, wait a minute, I'm not going to push you on that yet. Let me do one other thing, and that is to say that 99.75% of the data falls within 3 standard deviations of the mean. That means, for instance, that on the SAT test, about 99.75% of the data, people will score between 200 and 800. You could get an 800, maybe in an outrageous case you might get an 810. But if you think, I'll bet very few of you in the classroom here, and I've surveyed in the past, and I had 300 people in a lecture earlier today. 6 people in that lecture knew somebody personally who had scored 800 on the math portion of the test. That just indicates how relatively rare that is. If you can see where my pointer is on the screen over here, over on this side, that is to the right of 3 standard deviations above the mean, includes 0.14 part of the entire distribution. That means theoretically 14 people in 10,000 will have a score more extreme than 3 standard deviations out. That is, will score 800 or higher on that test. So it is a very rare event. Now, up to this point, we have been talking only about your raw score, and that's meant, as I've indicated, that if you tell mom, well, I got a 35 on the exam, and she goes ballistic, and then you say, well, but the mean was only 30, then she relaxes. But she shouldn't relax, because it may be that the range is from 0 to 100. And so you're only 5 points above a curve that goes way, way up. So the second thing you need to know is variability. It turns out there is a score that folds all of that data into the general fact that we give you, and that is what's called a normal score. Let me just review for you very briefly. 68% of the data falls within 1 standard deviation of the mean. 95% of the data falls within 2 standard deviations of the mean. And what percentage falls within 3 standard deviations of the mean?
99.3 quarters.
A bunch. A bunch. 99% plus is probably the easiest way to remember it. Now, so far we've only talked about, well, here's the range, here's the standard deviation, here's your score, and here's the group mean. There's an easier way to represent that, and that is to use what is called the standard score. If you remember the formula we were working with in the last lecture, what we were working with is exactly what on this distribution is simply x minus m, as you can see right here. This was the quantity that we were working with on the last distribution, on the last table of data that we were working with. Essentially, what we were working with was the deviation of each individual score from the mean. And if you remember, in that case, we were working with the weights of male students in a class. And there were 2 ways to actually report a given male's weight. One was to simply say he weighed 136 pounds, 30 pounds below the mean for the group. The other way to do it instead is to talk about distance from the mean, either negatively or positively. Okay? And in essence, to do that, whoops, I've messed myself up here. Let's go back a little bit to, I'm totally messed up here now. Give me a second. It's going to be quicker if I just take that off the screen, and I'm going to simply back up to there. We're going to go back into, hang on just a second here, we're doing a little quick computer work here. Let me go back and indicate that's the one I want, and we're going to put it right on screen there. See, now I hate PowerPoint. It's messed me up. The general point is that in essence on that standard score, or z-score, the x minus m quantity is what we're basically working with. That is simply the distance of a given score from the midpoint. So instead of saying that somebody's score is 136 where the average was 166, we could say instead his score was minus 30. That's essentially what the numerator in that equation tells us, is how far the score is from the midpoint. Okay? And a standard deviation then, what that formula does, that z-score, is nothing more than a unit that tells you how many standard deviations above or below the mean a given score is. So in essence, take an example of your raw score again. On the class exam I was talking about, if the mean is 30 and your raw score is 35, what that means is that your standard score is plus 1. And again, in terms of the formula that's on the screen there, the x, your raw score, is 35. The mean is 30. So in the numerator, we have a 5. And in the denominator, we said earlier that the standard score is 5. I'm sorry, the standard deviation is 5. So 5 into 5 gives you a plus 1. It is important when you report a standard score to indicate whether it's plus or minus. Because that, if you just say your standard score is 1, it doesn't tell us whether you're above the mean or below the mean. Okay, so you have to report a sign when you report a standard score. But if you simply go home and tell your mom your standard score on the first psych exam was a plus 1, what that's telling her is that you're at the 84th percentile. I'm not going to burden you with all the details about how we do that, but in essence we can convert mathematically, and there are tables that are generated to tell you what the percentile rank actually is, where you are percentage-wise on the distribution. The way I got that, if you think back or look back at the normal curve, is simply that in a normal curve, as you remember, the mean, the median, and the mode are stacked right on top of each other. And that means in terms of the data of a class distribution, half of the data is below the mean, so we've got 50% there. If you're at plus 1 standard deviation, it means we can take the 68% that is within 1 standard deviation of the mean, cut it in half, and add it to the 50% we've already got, meaning that you're at the 50th plus 34% at the 84th percentile of the overall distribution. Okay, so the standard score actually tells you a lot of information relative to your position relative to the group as a whole. And that's true whether it's a test score, how high you jump, how tall you've grown, anything we want to measure. All of those are features that are generated out of the normal distribution. Now, with that in mind, rather than cover the guts of inferential statistics, what I'd like to do instead is to talk simply about ways in which you can increase the likelihood that you've got a significant difference or a significant effect in an experiment that you run. Let's go back to the Crest toothpaste experiment that we were talking about the other day. If you go to Clinton, Tennessee, and run an experiment where you've got 100 kids that do Crest with fluorostat, the magic ingredient we're testing, and the control group does Crest without fluorostat, the thing that we're really interested in is, does that fluorostat ingredient have a significant effect? That is, does it drive the difference in that group far enough away from the control group that we can have some confidence that, in fact, it didn't occur just by the normal wandering that we were talking about? That is, that it's not a chance effect, but rather that our independent variable was what moved it, whatever distance we find. You're assessing the likelihood that that will happen when you do an inferential statistic. I'm not going to discuss any of those. We run entire courses at the upper undergraduate level on how to do inferential statistics, so I won't launch that today. But I will point out that when you run an experiment, there are three things that you're looking for which will, in fact, increase the likelihood that you've got a significant finding. One is to make sure that you increase the group differences. That is, what you want to do is to increase the difference between the two groups. That's in the numerator of the z-score that we were looking at. It was x minus, well, from your side, x minus m. Okay? The bigger that difference is, the more likely you've got a significant difference. As an example, on the Crest toothpaste, suppose we'd run 100 kids in a town in the experimental group with the extra ingredient fluorostat and 100 without. Okay? And we find every single youngster that brushed with Crest with fluorostat or fluorostat, whatever they're calling it, has one cavity. Every single kid. However, every single kid who brushed with Crest without fluorostat has two cavities. So we've got the difference between 1 and 2 cavities, and if you tell me how many cavities your kid had, I can tell you which group they were in. Okay? If on that basis, I say to you, brushing with Crest with fluorostat is a significant retarding factor on cavity control, would you tend to endorse that statement? Would you tend to believe that? Would you be more likely to believe it if, in fact, every single kid with Crest with fluorostat had one cavity, Crest without fluorostat had 5 cavities? Would you have greater confidence in my statement then that that extra ingredient has a retarding effect?
Yes.
Thank you. I was going to outweight you otherwise. Yes, one of the ways to increase the significance or the likelihood that you've got a significant finding is to do things in the experiment that will increase the difference between the groups. That's in the numerator of an inferential statistic. Okay? A second way to have that effect is instead to decrease the variability. The second way is to decrease the variability. Now we're in the denominator. If you remember on the standard score, the measure of between groups, the difference between you and the mean, was in the numerator. The measure of variability for the group that you're in is in the denominator. A second way to increase the likelihood that you've got a significant difference research-wise is to decrease the variability or reduce the standard deviation. Okay? That goes into the denominator. Those are the two most important ways to register an experimental effect. There is actually a third way that we could also talk about, and that is to increase group size. But that's almost cheating. I'm gonna show you an experiment a little bit later this semester, near the end of the course, where this group studied 250,000 families and found differences in IQ on the order of a quarter point. But they were significant. That is, the variables that they were measuring were actually significant because they had this whopping group size. That's kind of dishonest. I mean, it's legitimate, but it's a kind of a cheating way to get to the effect that you want. If you've got a really legitimate experimental effect, it should show up in a markedly smaller number of subjects. But any of those three variables, increasing the group size, decreasing the stability, or increasing the differences between the two groups, all will lead to having a more significant effect, basically one that is more likely to be true rather than attributable to chance. Now let's jump over and look at predictive statistics. In this case, What I want to talk about then is what's called a correlation coefficient. Okay? The correlation coefficient basically is going to give us two pieces of information about any data that we're calculating. One thing it's going to tell us about is the nature of the relationship that exists between the two variables that we're measuring. Okay? So one possible relationship that we may find is what we'll call a positive correlation. Two sets of data which are positively correlated with each other. Okay? An example of that would be the relationship between our salary and our tax. In general in this country, if you're not yet rich enough to hire an accountant or a lawyer, the more you earn, the more salary you're going to pay. Okay? So that's a set of data that is positively correlated. I could plot any of you here on the x-axis, and if this is your salary, I can predict anywhere between here and here as the likely tax that you're going to pay. That's pretty large. So what we do instead is to calculate a correlation coefficient. We take this data, and you'll notice there's kind of an elliptical shape to it. That's a positive correlation where the two variables increase. So we can actually draw an ellipse around this data. And the narrower this dimension of the ellipse, with data pointing in this direction, the more positive is the correlation that we have. But in this case, there is a general positive correlation between salary and tax. Okay? Salary doesn't cause tax, governments do. So it's not necessarily a causative relationship, but they are nonetheless, as you would understand, positively correlated. As your salary goes up, your tax tends to go up. As your height goes up, your weight tends to go up. That's another example of two variables that are correlated. We can actually draw a line to make a prediction. I'll show you how to do that here in a couple of minutes, but let me just move beyond this and move to a second type of correlation where the nature is not positive, but now in fact it's non-significant or non-existent or zero. An example of that here in Houston would be truck speed relative to the load of the height that is being carried by that truck. Okay, I can show you trucks that are moving very slowly on the interstates that may have a very low load height, or another one that's moving just as fast that may have a very high load height. Likewise, I can show you one that has a very high load that's moving either very slowly or very rapid. I should say one that's moving fast that has a load height that is low or very high. So in essence, in this case, we can summarize this data as being zero correlated. That is, they are non-significantly correlated. Knowing the speed of a truck is no help at all in predicting how high the load that it's carrying. Okay? And in this case, we can summarize the data with a circle, or you could even draw a square if you want. It doesn't, knowing the truck speed is no help at all in knowing where to predict the load height. Okay, so that's non-correlated data. The third possibility is to instead talk about a coefficient of correlation which is negatively related, a negative correlation coefficient. Now we've got the following kind of a relationship. For men who have a genetic inclination toward baldness, as age increases, the number of hairs on head falls. Pun intended. Okay? Basically, for those men who have a genetic gene toward baldness, the older they get, the lower the number of hairs that we'll expect to find on their head. If we do a hair count, we will expect it to be lower the older the male is. So in this case, we can summarize this as a negative correlation, and in fact, we can enwrap this data in an ellipse again. Now it's shaped in the negative direction. As one variable increases, the other one decreases. But we've got the same basic relationship here, an elliptical set of data. The tighter, the narrower this dimension of the ellipse gets, the higher the correlation. If we were to put, in physics, if we were to put pressure here and volume here, we would find a perfect negative correlation. That is, we wouldn't need these dots, we'd have a line. Basically, it would be a law rather than a correlation coefficient. In that case, if I know the starting volume, you give me the pressure, I can tell you exactly what volume you'll have at any given point. And in fact, in this case, for prediction purposes, rather than simply saying, okay, the age is here, that means the number of hairs on head is somewhere between here and here, what we do instead is create what is called a regression line. And what that regression line does is to essentially summarize the data in this way. That is, we collapse all this data on what is usually called a least squares solution, which you don't need to worry about. But that becomes our prediction line. So if you give me an age, I will then go to the line and come straight across and predict that this is the number of hairs on that male's head. Okay? This is negatively correlated data. It's important to understand that you can predict just as well with a positive correlation as you can with a negative correlation. It doesn't matter. It's the size of the correlation that is important, and that actually becomes the second variable that we need to understand, and that is that the magnitude of the correlation can be anywhere from -1, a perfect negative correlation, to +1, or a perfect positive correlation. Both of those are perfectly consistent or perfectly equally useful for purposes of prediction. Okay? The one other thing to leave you with, and we're having a little fun with the PowerPoint here as we gradually grow to understand it, is that a high correlation does not imply causation. Correlation and causation are not related. To give you an example, we know from a great deal of work here in college that there is a significant negative correlation between amount of beer consumed in gallons calculated annually and grade point ratio achieved. Okay? There is a strong negative correlation between amount of beer consumed in gallons annually and grade point ratio in college. Does that mean that beer drinking causes low grades? And if not, what does? Everybody's like, oh gosh, I've never drunk.
Drinking beer does not cause bad grades, lack of study time.
Bingo. It's the lack of study time, exactly. So we could probably argue that the more time you spend talking on the phone, the lower your grades, unless in fact you're talking to somebody about an assignment of some sort. But essentially anything that chews up time reduces your grade point ratio. So the beer drinking does not cause lower grades. Rather, it is correlated with lower grades. Higher beer drinking, lower grade point ratio. So there's a significant negative correlation there, but the one does not cause the other. And that's important to remember. Anytime you have a correlation, it doesn't matter what magnitude it comes in, what level it is not a causative relationship, it is correlational. Okay, now we're going to move into developmental psychology, our subject for today. And I want to pose three situations to you, first of all. What I'd like to do is to set the following kind of a scenario for you. Let's suppose that a mother and her daughter and you are waiting at the bus stop out by the Galleria on a hot, muggy August afternoon. You've been shopping for 3 hours. The mother and daughter have apparently been shopping for a long time. Everybody's tired. You're in the metro shelter and the sun is beating down on it, frying you. You're hot, you're miserable, you're tired. The 2-year-old is a little cranky, also hot, also tired, and it turns out hungry. So the 2-year-old turns to mom and asks for a piece of candy. And mom says, as moms usually do, not now, dear, it might spoil your appetite. Let's wait till after supper, eat a good meal, we'll give you a piece of candy. And the result is the 2-year-old pitches a hissy fit, kicking, screaming, questioning mother's lineage as only moms can, as only daughters can. And the net result is, how do you analyze that data? To what do you attribute the 2-year-old's behavior in that particular situation? To what do you attribute it?
Stress.
Maybe stress, yes, that's the basic thing. What would we normally call that kind of behavior on the part of a 2-year-old who's screaming and kicking and acting up that way? Yeah, it's a temper tantrum, a pure and simple temper tantrum. Who fixes that? Who's responsible for fixing that?
Mom.
You going to do it? Mom, of course. It's mom's daughter. It's her problem. Let her deal with it. Okay? Same bus stop, same hot, muggy August afternoon. You're waiting for the bus. The bus is late. Everybody's hot and miserable. You're waiting with a 22-year-old who has been shopping with her daughter. Okay? With her mother, I mean. That 22-year-old, hot like the rest of us would be, turns to her mother and says, "Can I have a piece of candy?" And mom says, as moms always do, "Not now, dear, it may spoil your appetite. Wait till after supper, you eat a good supper, we'll give you a piece of candy." And the result is the 22-year-old pitches a hissy fit, kicking, screaming, questioning mother's lineage as 22-year-olds learn to do. How do you describe this behavior? Is this normal behavior for a 22-year-old?
Craziness.
Of course not. This is crazy behavior. This is psychopathology in operation here. So we call the people in the white coats and get her to the help that she clearly needs in that situation. Bit of an overstatement. Same bus stop, same hot, muggy August afternoon. You're waiting with an 82-year-old who has been shopping with her daughter. Everybody's hot, everybody's miserable, the bus is late. The 82-year-old turns to her daughter and asks for a piece of candy. And the daughter says, as daughters learn to do, "Not now, dear, it might spoil your appetite. Wait till after supper, eat a good meal, we'll give you a piece of candy." And the result is the 82-year-old pitches a hissy fit, kicking, screaming, questioning daughter's lineage as only 82-year-olds are able to do. How do you describe that behavior on the part of the 82-year-old?
Old age.
Old age, there's another word we use normally.
Seniality.
Senility, right. The lady is senile. Okay? Now, the point is that in all three scenes, given my linguistic limits, I tried to describe as close to the same situation as I could. Okay? And yet in one instance, you were quite willing to call it developmental, you were quite willing to call it temper tantrum. In the second instance, you were trying to call it psychopathology and we need to go get help for the daughter. And in the third instance, you were going to call it essentially senility. So the same behavior at three different ages is labeled three different things by us in that particular situation. And I now understand why there was such a long pause when I did the 82-year-old, because I was the one who was supposed to supply this image for you, and we'll get to show it to you now, just so that you're convinced that in fact our artist can in fact render old people. If I can get the right thing on the screen here. Okay, so the 82-year-old also pitches a hissy fit as we're talking about it. The point is that that is the bottom line lesson of developmental psychology, and that is that the age that is appropriate for us the behavior that is appropriate for us at one age is not necessarily appropriate for us at another age. And in essence, that is what developmental psychologists study, is the changes in behavior that occur as a function of age. So in essence now, if we look at the history of how we got to the study of developmental psychology, it basically falls out into several markers that we can mention. The earliest developmental psychologist, and of course he was called many other things, is Plato, who in the 4th century BC proposed the existence of three different kinds of people. And our slide will actually illustrate this for you. He talked first of all about artisan workers. This was members of the working class, and I think we have a slide that will illustrate that for you. The artisan workers were basically people like you and I, the people who produce the material goods of society and in fact who consume most of them. But that's the vast majority of people, according to Plato, as he was writing in the Republic, in his book called The Republic. Do we have a slide for that or not? And then secondly, he also proposed the existence of what he called athlete warriors. The athlete warriors are basically a limited subgroup of the artisan workers. Okay, the warriors were basically a class that you could get into, according to Plato, by being able to reach or achieve certain performance levels. And he actually laid out a series of performance statistics on what he thought people ought to be capable of doing. Certain number of chin-ups within a given amount of time, certain time on the 100 meters, and so forth and so on. So he actually laid out what he thought was necessary in order to become a warrior. What he did thereby, in distinguishing between the working class and the warriors, or the military, was to establish an environmental difference, what we would call in modern times nurture, a difference achieved through nurture. That is, if you were a member of the working class and thought you wanted to be a member of the military, all you had to do was practice those arm lifts and the push-ups and whatever else he was writing about long enough so that you could reach the level that was necessary or required to be in the military. That is a difference attributable to environmental experience or nurture. But he also referred to a third class of people, and that is what are referred to as the philosopher kings. The philosopher kings was a group, a class, that you and I could not belong to until and unless our parents had been in that class. That is, that was a right that was achieved by inheritance and inheritance alone. Now, it's not inheritance in the sense that you and I use it in modern times, but it was nonetheless a right of inheritance. That is, that you could become a philosopher king if your parents were a member of that class. That was something that you inherited through nature, through inheritance, through heredity. And in essence then, what Plato did in the Republic in the 4th century BC was to identify one of the major arguments or issues in modern day psychology, particularly developmental psychology, and that is the nature-nurture issue. So it was actually way back in the 4th century BC. Now what we're going to do is to jump to a second person in the more modern times, and that is basically Gregor Mendel, who lived in the early 1800s. We also have a picture of Mendel at his finest. And in fact, there you see him. His primary contribution, as you know, was to write a description of the modern laws of heredity from having studied the garden pea. And although his was a very simplistic analysis, it was really the touchstone, the founding point of modern-day genetics. And so he did a major contribution toward our understanding of the basic mechanisms by which organisms are created from other organisms. This, in turn, was followed by another person, and that is a person whose name you will doubtless remember, and that is Charles Darwin. Darwin, in 1859, published his theory of evolution. And Darwin's theory was essentially the arrival of modern science. It represented the arrival of modern science in the current era. His father once said of him, "You care for nothing but shooting, dogs, and rat catching, and you will be a disgrace to yourself and your family. You think you have troubles." Darwin ultimately took a journey on the HMS Beagle given to him by his father, because the family was quite well off. He took with him a number of notebooks and a lot of pencils and observed wildlife all over the world. And the net result was that what was published in 1859 as a consequence of these journeys was his theory of evolution. That theory basically has three components to it that we can talk about. The first of these is heredity. And there is a very nice quote, which we'll put on the screen, that basically captures the essence of what is involved in heredity. It was essentially the modern application of Mendel's earlier work, and that is that the egg is but an egg's way of creating another egg. The emphasis there is on the message rather than the messenger. You and I tend to get all proud and puffy about how beautiful or handsome we are. But in fact, the only contribution you and I directly make to the human race is the genes that we pass on in terms of any hereditary effect that we have. And so in essence, the really important link from you to your parents and from you to your children is simply the genes that were passed on to create you and those that you pass on to create your children. And that's all. That's the only direct impact that you and I have on heredity, with a limited number of exceptions. The second element of that theory is variation. So he talks about heredity and the impact of that. And then Darwin also talked about the importance of variation. You look around the next large lecture class you're in, and you'll have several hundred people sitting around you who represent the end point of maturation. And each of us then is a combination of genetic messages from our mother and our father. We are the current representative, and we in turn pass those genes on to the next generation. But there are two major sources of variation. The processes of mitosis, meiosis that lead to the splitting of the chromosomes into each individual, involving the group that is used to create each individual sperm and egg, is only half of the total that each of us carries in our cells. And that half is combined with the half from the reciprocal egg that sperm joins, and that creates variation. That is, the splitting process itself is a random division of which dominant, which recessive genes go into the sperm or egg that is involved. The other form of variation that is also important is who you actually select to mate with. And that's where a second amount of variation also shows up. That's what you can see when you look around the lecture hall, is all the other examples of mature organisms with whom you might mate, presumably half of whom you might mate with. Those two elements, heredity and variation, are as plain as the nose on your face. In fact, they determine the nature of the nose on your face. And those are not arguable. I mean, those are as well demonstrated as the law of gravity in terms of modern science without any difficulty. The only part of that theory that has really caused difficulty is a kind of a logical derivative of the first two elements, which are very clearly demonstrable. And the third element is what is called natural selection. That is a very controversial part of the theory. It's kind of a logical extrapolation from his theory, but what it basically argues is that there is naturally genetic variation, that is, in the variation of genes that come together to form each of us. Some are strong combinations, some are weak combinations, and the particular organism may or may not be particularly well adapted to surviving in the environment that he finds himself in. There is one very popular and I think reasonably well documented theory about the disappearance of dinosaurs. That a meteor hit the Earth, created a huge amount of dust, which was tossed into the air, and basically was in the air for some several years. The net effect being that it was so dark that plant life was basically actively suppressed, and therefore there wasn't enough vegetation to feed on, and dinosaurs essentially disappeared. That was an instance where the dinosaurs genetically were not equipped to adapt to the environment as rapidly as was required by that cataclysmic event. So natural selection is the controversial part. There is one species of bees, for instance, which mates or which creates each generation at the time the queen bee decides to leave the nest. And what happens is that she flies straight up. And of course there are a whole bunch of beady-eyed male bee workers following along behind her with lust in their mind. Who actually she mates with is determined by the last male worker who is still flying on her vertical flight. And she actually mates with the last bee who can stick with her in that flight upward bound. He may be too winded to do anything for several minutes afterwards, but eventually that is the bee who fathers the next generation of bees. And so in essence, natural selection in that case is obviously partly genetics. Whoever has the best balance of wing structure and size and developed body and so forth. But it's also partly by accident. That is, whichever worker has most recently eaten what turns out to be exactly the right balance of energy doesn't have to carry anything spare with them. I mean, somebody who's just finished pigging out in the nest is not going to win because they're going to be carrying too much energy and too much weight, and they won't make it. So it's some kind of combination of accident and natural selection. But in essence, the net result there is that is the only controversial part of the theory. The other two are as well confirmed as anything in science. Darwin's theory of evolution. There's one other person that we can also talk about, and that is basically a person by the name of G. Stanley Hall, who died actually in 1924. He was a Renaissance person. Basically, he was a president of Cornell University. He was the founder and first president of the American Psychological Association. And in fact, he established the first developmental psychology lab in the country. His lab at Cornell was among the first. Not among the first, it was the first lab dedicated specifically to studying the interaction of the change of behavior as a function of age, the bottom line lessons of developmental psychology. Now, in terms of the research methods that we use, there are basically several that we can talk about. One of these is what's called the case study technique. When we use the case study technique, we don't use it in developmental psychology. So case study technique, though it might look tempting, doesn't work in developmental psychology. It's excellent for clinical psychology. It doesn't work in developmental psychology. So we do not tend to use it there. Rather, the kind of technique that we do tend to use instead, one of them is what's called a longitudinal study. In this case, what you're doing is studying an individual or group of individuals over an extended period of time. The key way to remember it is long in longitudinal, as in long-term study. The penultimate example of this was a study started by Lewis Terman at Stanford University back in the late 1930s. He identified about 500 children of Stanford faculty members and assorted other people in what later became Silicon Valley, and those people were studied over a 60-year period. And in fact, just within the last 5 or 10 years, I mean, Terman is long since dead, but another investigator at Stanford picked up the results and maintained the database. And we've actually had another study out within the last 10 years that is looking at that group of people who were who were younger than 5 in the late 1930s, who are now entering their 60s and in terms of their skills and so forth. That's a classic example of a longitudinal study. The disadvantage is that it's expensive and it's subject to any bias. That is, it's no more current than the discipline was when the sample was originally drawn. But the advantage is that each person serves essentially as his or her own control, and it allows for studying the impact of early effects on later life. The primary drawback with longitudinal studies is what is called the cohort effect. The cohort effect basically is illustrated in the following way. One of the concepts that we study in psychology, in developmental psychology, in learning and memory basically, is what's called flashbulb memory. Other than the September 11th disaster, for my generation, the most commonly cited flashbulb memory is a memory of the assassination of John Kennedy. That was a turning point in our culture, and you talk to anybody who's my age, 60, about that, and they will tell you that in all likelihood the most commonly mentioned flashbulb memory is John Kennedy's assassination. I can tell you who I was with, I can tell you where I was and what I was doing when I first learned by television that he had been shot in Dallas. That's a flashbulb memory for my generation. Most of you viewing the tapes were not born when Kennedy was assassinated. In fact, it may have been half that time since then had expired before you were born. So Kennedy's assassination simply is not part of the experience that you've had growing up. But you've had other experiences. The Oklahoma City bombing, you were likely aware of, and a number of things like that. Challenger disaster may be pushing it back to the early limits of your memory. But those are the kind of things that younger people would cite as key events in their environment, in their growing up. So the net result is that each generation actually grows up with a slightly different set of experiences impacting it. I've talked to several people my age who, when closing down their parents' houses, which I had to do about, I closed it down about 7 or 8 years ago now when my second parent died, I was amazed when I went in there to find that there were 3 operating and stocked refrigerators in the house. Actually, really 3.5, because it was one of those little bar refrigerators also, which was fully stocked and functioning so that you could have gone into any of those refrigerators and eaten anything in there, whether it was in the freezer or the refrigerator. And I've talked to other people my age, several of whom have had the same experience. In contemplating it, I think the basic reason for it is that my parents were in their mid or early teens when the stock market crashed. Now, unlike the difficulties that we've had in more recent times where 5 or 6 or 7% of the population is out of work, then about 1/3 of the population was unemployed, and it was a major financial disaster for the entire country. The rich were no longer rich and the poor were destitute. And, providing a living and putting food on the table was a real challenge at that time. And so I have a feeling that for people who were that age, one of the protections that they developed, perhaps without even being consciously aware of it, was, I'm going to make sure there's plenty of food in the house all the time. So there's always something there to eat. That's a cohort effect, okay? It's a drawback in longitudinal studies. By the way, as a review, is that a between subjects or a within subjects design? Is a longitudinal design a between or a within subjects design?
Within.
Yes, that's a within subjects design. Okay, it's the same group studied over an extended period of time. Next possibility is, instead of looking at longitudinal study, what we can do instead is to look at a cross-sectional study. Cross-sectional study is where we take a group of people at each age level. One study we're going to review down in the section on intelligence involved finding a sample of 50 people who were age 25 and giving them an IQ test within about a 2-week period. Another sample of 30-year-olds, 50 of them was found and tested, all the way up to age 70. So they actually had 500 people in this study. Every one of them had their IQ tested within about a 2-week period. And then what they did was to calculate the average IQ for each 5-year increment and publish it. That's a cross-sectional study. There is a major disadvantage there, and that has to do with the fact that the environmental experience that you have is, I just realized I made a mistake. The cohort effect I really should have talked about bears on a cross-sectional study, not the longitudinal study. Let me correct that. On the longitudinal study, since you're studying the same group of people over an extended period of time, what you're going to see is the effect of each environmental event on the subsequent life that those people utilize or experience. So that particular cohort might, as in the example I gave of the stock market crash for people who are now in their 80s, would have involved an effect that would carry over in that lifetime. But the cohort effect is most problematic for the cross-sectional study, and you can see why if you think about it. Somebody who's 70, when this study was done on testing intelligence, would have had the stock market crash in his or her history. Somebody who was 30 when that study was done would not have had it. And more particularly, education has gotten markedly better over the last 50 or 60 years. So that people who are 25 now are much better educated than people who are 70 now were when they were 25. So if you find some decline in IQ as a function of age, it may be attributable only to different quality of education, not to any direct effect of aging on intelligence. Okay, so scratch what I said earlier and register the cohort effect as a problem in cross-sectional studies. Okay, I'm going to criticize and explain that study more fully when we get to it. But a cross-sectional study has different representatives at each interval. The advantage is it's quick and dirty. The disadvantage is that it is subject to the cohort effect. The third type of study that we can also mention here is the cross-sectional study. In a cross-sectional study, well, I've already mentioned that. Let me move on here. I'll eventually get caught up with myself here. The third type that we do use is what's called the self-report study. And in essence there, the data collection process involves basically surveys, questionnaires, interviews, and so forth. Now, you might think to yourself, well, that doesn't really sound very different from a case study technique, and in some ways it isn't, because we're still collecting data individually from people in this particular kind of self-report technique. But the primary difference is that by using the data collection technique of surveys or questionnaires, what we're doing there is that some factors, you can make a good compromise between longitudinal and cross-sectional studies. With a self-report or a questionnaire-based survey, the problem is that it still relies on people's memory. But the way we try to correct for that is that instead of studying an individual case extensively, what we do is to survey broadly across individuals, and hopefully we can eliminate the cumulative effects of unique memories in that kind of a situation. So those are the three techniques that we most frequently tend to use. That is longitudinal studies, cross-sectional studies, and self-report studies. There is, as a kind of an interesting extension on what I was saying there, there is a very interesting compromise that has been worked out in the intelligence study that I was talking about earlier. That is, if you remember, they started with a cross-sectional study and in fact looked at and reported the data only as, here's what 25-year-olds have for an IQ, here's 30-year-olds, here's 35-year-olds, here's 40-year-olds, and there was a decline. The criticism that was registered on that study, as I said, was the cohort effect issue and the issue of the impact of education, which was hard to eliminate. What these investigators did, rather interestingly, was to go back and combine the cross-sectional and the longitudinal approach. What they did was to go back about 5 or 6 or 7 years later and retest as many people as they could find out of the group that they had originally identified. Okay? In that particular study, as I remember it, and I'm doing this strictly from memory, they were actually able to track down about 60 to 65% of the sample. 64 is what sticks in mind, but don't quote me on that. But in essence, so they retested. If they had 50 people in each group, they had an average of maybe 30 in each of the 10 groups that they'd tested. And then what they did to plot the results is where they really got clever. And you'll have to hang with me here for a minute to understand what they did. Let's say that the 25-year-old group had an average IQ of, say, 107 when they plotted it 25 versus 30 versus 35 versus 40. Once they had the second reading of the IQ for that group, what they then did was to say, okay, here's the average IQ for the 50 at age 25, here's the average IQ for the 30 at age 30, after they've grown 5 years. The way they decided where to plot the results for the 30 was anchored on where that group had been 5 years earlier. Okay? So in essence, what had happened when you did it purely cross-sectionally, the data dropped. That is, IQ from age 25 to age 70 was on a steady decline. What they found, however, was that if they plotted it in a cross-sectional manner with this kind of a linked longitudinal control, what happened was that if you compared this group relative to where they'd been 5 years earlier, their IQ had gone up slightly. And if you then looked at the 30-year-old group and anchored the now 35-year-olds and where you plot them, their IQ relative to what they had known 5 years ago had also climbed slightly. So in fact, what they created is what we could call, if you want, a technique that's kind of halfway between longitudinal and cross-sectional study. The technical name that is often applied to that procedure is what's called a linked longitudinal control. And when you use a linked longitudinal control with that experimental data, what you find is that IQ actually climbs with age up to about 60. and then decline slightly, as we'll see when we get into testing. There's some probability that it's simply lack of interest. By the time you're 70 years old, you give a rip what your IQ is. You've already had a lifetime profiting or suffering from it. And so there may be a kind of a fall off in motivation toward the latter end of that study. But that's an example of a linked longitudinal control, and some of the studies we'll look at this semester in developmental psychology will profit from that kind of building on the earlier idea that we only use longitudinal cross-sectional studies. We'll launch into theories of developmental psychology in the next lecture.